Okay, so hopefully everybody can see my screen. Perfect. Sorry. uh, so welcome everybody. Welcome to our new seminar series. New semester brings in fresh faces and exciting times to meet new people and their research. And so we are very happy to bring Dr. Hanping, and he's one of our new faculty members at the School of Aerospace and Mechanical Engineering. So, but before we start the seminar, I would like to introduce you the graduate student community and how to connect with us and some of those important things. So Rachel, who is on the call, and we both are co-chairs for the graduate student community this year, and this is our leadership team. So we have some of the graduate students who are volunteering to help build this community and also help us organize some of these events, especially the seminar series. And it would not be possible without their support and help. So we are really thankful to them. And so Avinash and Andrew are responsible for publicity. So most of the uploads of the videos as well as some of the emails that you get would be coming from these two people. Swapnil and Filani are social events coordinators. So we do some of the social events where we do International Food Festival, and we also do some fun game nights as well. So they are responsible for making that happen. Mayank Anirban and Nurayan also help us in some of the other activities such as treasury. And our faculty is Farooq Misri. And so we are really happy to be a small team, but a really strong team. So there is one small change in our regular timings that we meet. Earlier, we used to meet at 4 p.m. on Fridays, but that wasn't a possible time. So we're meeting on Wednesdays at 5 p.m. And so if you want to be a part of the leadership team and if you want to work with us, you could always join us to the meeting. All you have to do is write to me or Rachel. Our email IDs are here, and we'll get you the link for the leadership team meetings, and then you can be a part of it as well. So if you are not a member of GSC yet on the Engage page, I would ask you to please scan the QR code and be the member. This way we are able to show the graduate students in it that our roster is full and we have people who are participating, and that way it helps us secure funding to do seminars like these. So your support is really important to us. And so if you could take some time, and if you can scan the QR code now or just go to the Engage page, type graduate student community and join us. We'll be happy to have you on our roster as well. So we have a Facebook page, and so every seminar that we do has a Facebook update of who is going to be the who is going to take the seminar and what the seminar would be about. So if you want to know more about these, if your email is not accessible to you, you can still get these notifications on Facebook. We also have a YouTube channel, and so if you've missed a seminar and you want to go back to watch any seminar that has been from probably fall 2020 or so, we have those seminars on our YouTube channel. And so you can go back, look at some of our previous seminars. There are some beautiful seminars that are out there waiting for your eyes to go and see. And so we would like you to go check out our YouTube page as well. And so this is a graduate, this is a launch that is for the graduate students. And so the room is called Dave and Susan Bird Team Room. This is a space where graduate students can spend their time if they're on campus, or utilize the room if they need it for a meeting or so, or to do like homeworks, group discussions, anything like that. And so if you want access to this room, we would like you to write to Rachel or me, or even the graduate student community. All you have to do is send us your email ID, your name, and your OU IDs, and we'll make sure that you get access to this room specifically. There are also some rules to accessing these rooms, so that would be an attachment to your email with the access to these rooms. So this seminar will have a link to a Google form, which will record the attendance, and so that will help us get the emails of the people. So if there are new people on this list, then we will add them to our regular mailing list, and so that you can get notifications for future seminar series or any correspondence from GSC. And so today we have Dr. Hanping, and his topic of seminar is solid oxide cells for hydrogen production and beyond. And first of all, welcome to OU, and hope you're having a good time in Norman. And with that, I would hand over to you. Floor is all yours, Dr. Ding.
Thank you so much, Roshan, for the introduction. Yeah, I'm so glad to give your talk today. Let me share my screen first. Yeah. Can you see my screen now?
Yes. Yes, sir. Yeah.
Okay, great. Yeah. So good afternoon, everyone. Yeah, I'm a new, assistant professor to the AME department. I have been here like, I think it's exactly 1 month. So I'm new to here. But today I want to give you some, some brief introduction about the hydrogen production via solid oxide cells. I try to modify some used slides and trying to give some, interesting and also fundamental, stuff, to, hope you like, today's presentation. So first is the outline. I will introduce some, the basics for the hydrogen production technology, which is a solid oxide cell. And then I will give you some examples, about the materials design and manufacturing, and also some three-dimensional electrode structure, synthesis, and also some other interesting topics, which is beyond hydrogen, but is still based on the solid oxide cell. So firstly, I want to give some very brief introduction about myself. So, my research background is basically materials science. Actually, I graduated, from the University of South Carolina, and with my, PhD degree in mechanical engineering, and I worked on the solid oxide fuel cell in an EFRC center, which was established by Professor Ken Snyder, and my supervisor was, Chris Xue. And after graduated, in 2014, I moved to Colorado School of Mines, and I work as a postdoctoral fellow, in Colorado Fuel Cell Center, to work for a few RPE and refuse project from the DOE. And after a short 3 years there, I moved to Idaho National Lab as a research material scientist. I have been there for like almost 5 years, and then I start my new journey in in OU. Yeah. Firstly, and then I want to introduce my research interest. So here I list some primary research interest I will probably focus on in AME, but it's not just limited to this area as listed here. So I will focus on firstly the hydrogen production, and also the carbon capture and storage, and fuel cell, and solid state lithium battery. I'm also very interested in advanced manufacturing, such as 3D printing and plasma sintering. And also I'm very interested in the area of so-called power to X, that is to make use of the renewable electricity and some feedstock to convert those energies to some chemicals which has a higher value. And lastly is integrated energy systems, which is about to make use of the nuclear energy such as electricity, also the high quality heat, and also from the solar panel, to integrate this kind of energy with, with a solid oxide cell to form a plant, for hydrogen production and also the chemical synthesis. So today the main topic is hydrogen. Definitely, I want to give some, brief, introduction about the hydrogen. So hydrogen technology is a very broad, topic, from the hydrogen production, storage, utilization, infrastructure, right? So it's very broad. So here, we will focus on, the hydrogen production, which is the starting point of the hydrogen economy. So if from in DOE, I want to say there is a hydrogen consortium, started at 2016, which launched the effort to fund the universities and also industry to focus on some primary hydrogen production technology based on the water splitting reactions. And since the launch of this consortium in 2020, DOE announced the hydrogen plan for next 1 decade. And just shortly, 1 year after that, DOE announced the hydrogen shot, which is still under the Earth shot, trying to bring the hydrogen production cost, from the current goal of the $2 per kilogram to $1 per kilogram in 1 decade. So this figure below shows all the roadmap for the hydrogen, on the where the hydrogen will produced, and also how we are going to utilize the hydrogen in the industry. For example, for fuel cell car, for the industrial such as steel manufacturing and fertilizer. And lastly, the OU also announced the task force by our vice president, about how we are going to achieve the hydrogen, economy in Oklahoma. So I'm hired by this, hydrogen cluster. So for the hydrogen, firstly, we have different kinds of the hydrogen. So hydrogen can be, divided into, by different color, from the gray, blue, turquoise, and green hydrogen. So how, we define this kind of the hydrogen, which is based on the feedstock and also, what kind of approach we produce the hydrogen. For the green hydrogen, as you see at the very right side, why we call it green hydrogen is because we just use the water as a feedstock, not just the methane. Because right now, 99% of hydrogen is produced through the methane steam reforming reaction. So for this reaction, it contributes a lot of the CO2 emission. So it's not very sustainable. But for now, under the hydrogen economy, people also need to to get the carbon capture technology to be involved, capture all the CO2 emission from the industry. For the green hydrogen, we use another technology, which is water electrolysis. So we split the water, right, to the hydrogen and also oxygen. We can integrate the energy, from the renewable, such as the wind, the solar, and even the nuclear energy, So under, the category of the water splitting reaction, right now DOE focus on the 4 kinds of the technology under this hydrogen consortium. One is a low temperature electrolysis, high temperature electrolysis, photoelectrochemical, and also solar thermochemical. And most of the investment go to the low temperature and also the high temperature electrolysis technologies. Later, I will say why, as you see, when, as you may hear that like a Toyota, they manufacture the fuel cell car, which is based on the low temperature fuel cell technologies. And the electrolysis is just the opposite reaction of the fuel cell process. And today we are going to focus on one of them, which is called high temperature electrolysis technology in the solid oxide cell. Why is it high temperature? Is because for the low temperature is based on the operation under at 80 to 100 degrees C. And for the high temperature electrolysis is from the 600 to 900 degrees C. So that's the reason we say it's a high temperature water electrolysis. So for these pictures shows the structure of the solid oxide cell. It contains a few layers of the ceramic layer. As in the middle, you can see it's an electrolyte, and at the bottom and also the top, there are 2 different electrodes. So the water will be fed from bottom side, and then because of the catalysis, water can be split at this few electrode site into the either proton and oxygen ions. Depending on the category of the electrolyte, either the oxygen ion will transfer through the electrolyte membrane to the other side to form the oxygen. And we have another kind of the electrolyte with a proton conducting electrolyte. So the proton can transfer through the membrane to form the hydrogen at the other side, and then the oxygen will simultaneously, associated to be oxygen. So this kind of water electrolysis is facilitated by both voltage and the heat, based on the basic thermodynamic. And this is also an electrochemical reaction, and the electricity is applied at the external circuit to apply the voltage onto the cell. And the hydrogen and the oxygen can be separated as each side of the electrode, so we can easily get the pure hydrogen. And more interestingly, later I will introduce some other kind of interesting reaction can be easily adopted, such as the syngas formation, and some higher value added chemical can be also synthesis through this solid oxide cell. So here shows the technical advantages why we use a high temperature electrolysis. This figure shows the thermodynamic for the steam electrolysis. On the top you can see the black one. When the temperature is higher than 100 degrees C, right? It's steam. And then you can see as the temperature is increased, you can see the slight increase of the total energy demand. And all the energy demand is consistent of either the electricity energy input and also the thermal energy input. That means that when the temperature is increased, we can make use of some high quality thermal energy to be supplied into solid oxide system, and then we can reduce the demand for the electric energy. So as a result of this, solid oxide cell, in short, we call it SOC, can achieve very high energy efficiency. And also because of this high energy, high temperature, we can avoid the use of the precious, catalyst materials such as, for the low temperature electrolysis technology, they need to use the platinum, to catalyze, to facilitate the water splitting reaction. In this case, we just need to use some very cheap, metal oxide material. So second advantage is the low cost. As I mentioned, we avoid the use of the platinum, group, a metal, as a catalyst. And we can also integrate the heat from the nuclear plant and also from the solar. And right now, I think we have some national labs, particularly some nuclear-based national lab, they are trying to advocate the integration of the nuclear plant and also the solid oxide cell system to make the green hydrogen. So this figure also shows, how we are going to, to integrate the nuclear and also the SOC to generate, the electricity dynamically, because, different, electricity demand, on the daily basis, right? We can make use of the extra electricity, to convert water to hydrogen, so we can store that energy. And so what it looks like for the SOC. So the top one shows all the component for the SOC. As you can see, for one unit, it consists of the 2 electrode, anode, cathode, and in the middle is the electrolyte. And in order to lay many pieces of the SOC together, we need to put the interconnector, separator in the middle of each cell, so we can collect the current density, voltage, and we can also feed the different kind of gas like the steam and also the carrier gas into the different side of the electrode. And right now we have 2 kind of configuration. One is a planar, so it's flat. So we can, right now in the industrial, we can manufacture very large, like a 15 centimeter by 15 centimeter. That's for the majority of the industry. But right now people can also manufacture even larger. So we can increase the active area, so we can increase the hydrogen production rate. The second one is a tubular SOC. Tubular SOC has some more advantage than the platinum because it's a more mechanically robust, and also it can be easily sealed. So it's more convenient to format the system. So for the high temperature electrolysis, right now we have 2 kinds of them. So one is oxygen ion conducting SOC, and another one is called hydrogen proton conducting SOC because of the different electrolyte in the middle. On the left hand, as you can see, is the oxygen ion conducting electrolyte. So the water is fed at the right hand side, and after the splitting, the oxygen ion trans through the membrane. And in the other case, the proton is transporting through the membrane. So what's the difference? You want to say why? So the table lists the difference between these 2 different kinds of the SOC. One is the operating temperature. For the conventional oxygen ion conducting SOC is operated at a higher temperature, like 550 to 750, even 900. Oh, sorry, it's the left hand, 650 to 850 degrees C. So it's pretty high temperature. This high temperature actually can increase the manufacturing cost of the system because we need to apply very expensive interconnect material. So the manufacturing of the interconnect material is very expensive. That can consequently increase the total cost. And also the high temperature can challenge in the materials system. the interface and also the compatibility between each different material layer. So if we can reduce operating temperature to be a little cooler, right? So it can reduce this kind of stress in the system. So for the proton conducting SOC, because the proton is smaller, so the transport of the proton through the electrolyte is easier, so which can reduce the activation energy for the proton transport. As a result of that, the proton conducting SOC can be operated at a lower temperature, which can relieve those kind of issues caused by the high temperature operations. Definitely, we have also some other kind of advantage. For example, for the proton conducting SOC, which can produce the clean and dry hydrogen, so without any kind of separation between the hydrogen and also the steam. So for a typical SOC, for each layer, electrolyte, fuel electrode, and oxygen electrode, what kind of material system for them? So later I will introduce a little more about the composition for the oxygen electrode. So for the electrolyte, we have, just as I said, two kinds. One is based on the zirconium oxide, doped with the yttrium, to form the fluoride type of the electrolyte, which can conduct oxygen ions. Another kind of is a proton conducting, which is mostly based on the barium cerate or barium zirconate, perovskite materials. And then we doped some transition metal into the materials to form the oxygen vacancy. And then that can, facilitate the transport of the proton. But for each layer, I want to, give you some very, simple, introduction. So for the electrolyte, it has to be very dense layer. So the hydrogen at one side, oxygen at the other side, they cannot penetrate through this electrolyte membrane. So we need to fabricate a ceramic dense layer in the middle. But for the electrode, fuel electrode or oxygen electrode, they have to be porous, and they have to be mechanically strong to support the entire device. So that can create some difficulty. How we are going to create two different kinds of the structure at the same time. That is a porous electrode substrate and also the dense electrolyte membrane. That's for one thing. Secondly is for the each component. For the electrolyte, it's just a single component of either fluoride or the perovskite material. And for the fuel electrolyte, is a mixture of the nickel oxide and the electrolyte materials. This is a very thick layer, which is to support the entire, the SOC. And the nickel oxide can be reduced to nickel during the operating process by the hydrogen. And then nickel is a catalyst for the fuel electrode side. And for SOC, what kind of challenging for now, in this research community, I divided into two different categories. One is a materials issue. Another, I put everything together as other issue. So for the materials issue, one is sluggish reaction activity, particularly for the oxygen electrode, because water splitting occurs at this electrode side, particularly when the operating temperature is reduced, the materials shows a very slow catalytic activity, towards the water splitting reaction. How we are going to, develop the new materials with a higher catalytic activity, Second thing is the chemical stability and also the interfacial stability, because we need to feed very, high steam concentration for the reaction, right? Under the very high temperature, the reaction between the steam and the materials can happen. That can lead to some formation of the insulating materials and then slow down the reaction. Second thing is, the thermal compatibility. We have different layers of the ceramic materials putting together. That can also challenge the compatibility, because sometimes we can see some delamination between the electrode and also electrolyte because of the thermal shock. And another is the interlayer diffusion. This diffusion is an element diffusion, because for each layer, it contains a different element. And then at a high temperature, the element can diffuse through the other layer, so which can cause some other kind of issue. Another important topic is long-term durability under the realistic operating condition. This realistic condition means a high temperature, high steam, and high current density, which can challenge, the material's stability. Such as in the long-term operation, we can see the coarsening of the nickel, particles. We can see some cracking in the electrolyte layer, as identified from people. And the last thing is efficiency. Efficiency. We also see some, leakage problem in the electrolyte, which can reduce the, energy efficiency. And from the other kind of aspect, we also have some, problem with the manufacturing. So how we are going to scale up from the lab scale to the industrial layer? Is your materials system feasible for this scaling up? That's a question. And also because when in the system we put a different component together, we have some other kind of poisoning phenomena, in the electrode, because in the interconnect component, it contains some chromium. So the chromium can evaporate and then form the insulating materials at the interface, and which can slow down the reaction. And some other things like expensive interconnected materials, and how we are going to integrate, how we are going to predict the degradation behavior, and also the thermal mismatch or the thermal gradient, which can also cause a failure of the SOC system. And then next, I want to focus on a material design of the oxygen electrode materials. As that this triangle, right? So the materials structure, and the processing can lead to different kind of performance. So how we are going to design rationally the materials composition, how we are going to take care of the processing where so we can yield the reasonable or the high performance for the SOC, for the hydrogen production. So for the oxygen electrode, most of the oxygen electrode are based on the perovskite materials. When you hear the perovskite, you may hear a lot for the solar, for the solar, cell, right? And the perovskite, also is commonly used for the oxygen electrode. So perovskite is a structure consisting of octahedral of the BO6. B is the metal at the B side, which is an octahedral structure, as you see here in the lattice. And then we have many, octahedral, stacked together. And between, these octahedrals, there's a very large space in between, which can, contains the A side cation there. And then eventually it forms the ABO3 perovskite structure. AbO3 is the simplest structure, but it's also the most common, structure for the oxygen electrode. Because for the perovskite structure, it has a very large tolerance factor. What is a tolerance factor? Tolerance factor is to describe how the crystal structure can be distorted because of the dopant as A side, B side, by the gas condition, by the temperature, all of the conditions and also the composition can cause the distortion of the structure. But for the perovskite, it has a very high tolerance factor. So you can dope many kinds of the elements. You can dope a large fraction of these dopants into the crystal structure. And then because of this kind of doping, you can tune your properties like the electrical and the mechanical and the catalytic activities. So you can tune these properties by changing the composition. And the perovskite can tolerate this kind of structural changes. And also because of this tuning, we can easily change the properties on the surface and also bulk to accommodate this application. This slide shows some, typically used, the structures, that like the perovskite, RP, rod less than copper. We typically call it RP structure. And for, among these kind of different materials candidate, as I mentioned, the perovskite is a main, material systems I have been studied before. So here, this picture shows the interface between the electrolyte and also the oxygen electrode. So when the water splitting reaction occurs on the surface, we want to know what exactly the elementary reaction step is. Quite complicated. It's also not easy to identify this kind of primary sub-steps for the reaction. But normally we believe that water splitting reaction, includes the water absorption on the surface and then dissociation. And this dissociation process is very complicated. For example, you have one proton, or the hydrogen proton dissociated from water molecules, and then and then from there we have more dissociation of the proton, and then combination of the two oxygen ions to form the oxygen molecules is quite complicated. And after this dissociation, we have the desorption of each species. So for the catalyst, it's very important to control this kind of absorption, dissociation, and desorption. So we want the water to be easily absorbed on the surface, but we don't want that absorption is very strong, because after the dissociation, if it's too strong and cannot desorb it very easily, it can further limit the further reaction. So we should find the good balance between the absorption and desorption. And so the surface property and also is very important. So we have a term called the surface exchange coefficient to describe, how frequent, for this kind of chemical reaction. Sometimes, as the surface is an important aspect, for the limiting step, which can, limit the overall water splitting rate. Another thing is a bulk diffusion. Bulk diffusion means that when you have the proton dissociated, you need to diffuse from the particles of the electrode, as shown in this figure, through either the surface or through the bulk into the interface, into the three-phase boundary between the electrode and electrolyte material. This is another complicated process, in the SOC processing. So next, I want to introduce a demonstration of a materials design, synthesis, device formation, and evaluation. So based on all the fundamental basis there, so how we are going to design a robust and also stable oxygen electrode. Here, this is based on my previous work. So in order to facilitate the fast hydrogen production rate, the conductivity for the electrode material is very important. Normally, right now, for the perovskite electrode is mixed ionic oxygen ion and also the electron conductor, which is a two-phase conductor. So which can limit the reaction on the surface of the electrode. Limited to the triple phase boundary. But if we can extend the conductivity to the three-phase boundary, three-phase conductivity, which is the oxygen ion, proton, and also the electrons, we can easily extend the reaction active side from the interface to the entire electrode surfaces. As figure A is showing that for the mixed conducting electrode, the reaction is just limited as an interface. But if we can develop a materials which can conduct this three-phase charge carriers, we can easily facilitate the increase of the active size. So how we are going to trigger the proton conductivity in the oxygen electrode, which is very important. So normally, for the proton conduction, it is from the formation of the proton defect. The proton defect is a chemical, is a defect reaction between the oxygen vacancy in the lattice and also the steam. When the steam fills the side of the oxygen vacancy, it can create the hydroxide in the lattice, and this hydroxide species can be established to form a bridge for the proton conduction. So in order to trigger the proton conductivity, we also want to hydrate the oxygen vacancies in the electrode materials. So here I proposed a parent materials is a praseodymium cobaltite material. It's a PR cobalt COO3, and then I doped with nickel with 50% as a B side. The reason is because I want to dope this 50% as a B side to trigger some changes. What kind of change? So firstly, I use some DFT to calculate the proton migration energy within the lattice before and after this doping. And then after the doping, as you can see, we can significantly reduce the energy for the proton migration from different coordinate through the octahedral, different octahedral size. And then we synthesize this material to form the right phase of the materials, and then to get the pure phase materials. And then we want to to prove the existence of the protons within the materials. Firstly, the high temperature XRD is used to characterize the in situ evolution of the crystal expansion during the process. We supply the steam into the XRD, and then we observe the shifting of the peaks upon the exposure time. So we can correspond this kind of lattice expansion to the hydration process of the oxygen vacancy. So we also use a TGA, to observe the weight change during the hydration process. As you can see, for these materials, PNC materials, it exhibited the most weight gain during the hydration process. We further examined the hydrogen permission, by fabricating the dense membrane of this electrolyte, these materials. And it also shows very much higher, hydrogen permission rate than the conventional hydrogen permission membrane. What does that mean? It means this electrode materials contains a mixed conductivity of the proton and also the electrons. So further, we use the FTIR to characterize the dehydration process. So if we have the proton stay in the lattice of the electrode, so how about we dehydrate the materials by heating the materials, and then we can use the FTIR, we can use the mass spectroscopy to observe this process. So when the material is upon the dehydration process, the FTIR can examine the hydroxide, the vibration of the hydroxide group. That means we have the water coming out from the lattice. So this is a reverse process of the hydration. So we also use a mass spectroscopy to characterize the exchange process between the isotope of the hydrogen. So we expose the material to the water, and then we switch it to the heavy water. So we can use the SMs to observe this kind of exchange between the H and the D element to prove the existence of the proton. After this material is synthesized, we can manufacture the SOC device. Normally, we use a roll-to-roll manufacturing process, which has been established in Idaho National Lab, which was my previous working place. So we use this capability to manufacture the green tape of the different component, such as the fuel electrode tape and the electrolyte tape. We can fabricate this kind of green tape with different thickness. So and then we laminate different green layers together to form one integrated layer, and then we put it into the high temperature sintering furnace to densify the electrolyte. And and after that, we can use either the laser cutter to cut each ceramic layer to form different customized size and also the shape. And eventually we use another step to screen printing the electrode slurry onto the half cell, and then to form the final product of the SOC. So before I introduce some typical performance for the SOC, I want to explain a little about how we understand the polarization curve for SOC. Here the x-axis is the current density, the y is the voltage. When we apply, for the right hand side is the fuel cell mode. That means the current density is positive. So this current density is from the electrons in the external circuit, which is spontaneously from the hydrogen molecules. So this fuel cell mode is spontaneous when you put a load, electrical load, as the external circuit. But for the left-hand side, it's the electrolysis mode for the hydrogen production. That means we need to apply external electricity or voltage above the open circuit voltage. So you can reverse the reaction from the fuel cell mode to the electrolysis mode, so we can split the water. So as I said before, we, for the electrolysis reaction, we need to apply the voltage and also temperature to facilitate the reaction. For each IV curve, it consists of different, overpotential or polarization resistance, which is because of the activation of the materials, because of ohmic resistance, because of the concentration of the mass from the mass transfer of the, of the gases. So all of the overpotential cause the non-linear curves of the IV curve. So later I will introduce a little more about this. So here, this slide shows some typical performance of your fuel cell and also electrolysis mode. So if you times the, the current density and the voltage, you can also form the, the power density. So we compared this power density with others to demonstrate, the advance of the materials development. So the left side of the figure A, you can see, the intercept is about 1.1. That's for the volt. That's open circuit voltage for the SOC. And in order to facilitate water splitting, you need to apply the external circuit. So we need to have the voltage above this open circuit voltage. And then we have the hydrogen produced from the water splitting reaction. And here I want to see this is the first demonstration of the self-sustainable operation of the hydrogen production. So this is a reversible process between the fuel cell and the electrolysis mode, so which is very interesting. So I applied the cell in the electrolysis mode for wire, and then we can generate adequate hydrogen inside the chamber. And then we reverse that process to fuel cell mode. That fuel cell mode can utilize the hydrogen generated from the electrolysis mode to form the electricity. In this process, all the hydrogen, external supply of the hydrogen is totally stopped from the gas cylinder. So we can claim this is a self-sustainable process. So we can achieve that, the hydrogen production and the electricity generation, simultaneously by easily switching, the working mode. This is a dynamic. That's what exactly DOE want to have, because we have we have the smart grid, right? We have different demand, for the electricity from the demand for the on the daily basis. We want to store those excessive extra electricity, from the grid, and then we can produce hydrogen and store there. And then when we want to use that electricity, we can convert that chemical energy stored in the hydrogen to the electricity by easily switching the working mode. So here it also shows some, the examination on the robustness, on the chemical and electrochemical, by changing the temperature, voltage, and also steam conditions, because these are the prime parameters, for the steam, in electrolysis process. So we changed the voltage, from 1.2 to 1.4 to 1.6. We changed the steam from 20% to 60%. We operated for different time period. We even changed the temperature to simulate the thermal shock or the thermal cycle, from 400 to 600 degrees C, to see how this kind of SOC ceramic structure can tolerate the thermal shock. Next, I want to, it's already 1 o'clock now, so I want to go a little faster. The second piece of work is the electrolyte work, So typically for the oxide conducting, one is a yttrium doped, zirconium oxide, which is oxygen conducting electrolyte. Another is a proton conducting, which is based on the perovskite materials. For all of these kind of electrolyte, we have some criteria for being considered as electrolyte materials. One is conductivity, electronic leakage, the stability, the mechanical strength, and also the manufacturing ability. So we need to make a complement in all the parameters. Eventually we can select the good materials. So for the electrolyte material, we need to densify the electrolyte, right? And we densify the electrolyte, and we want to achieve the high, the conductivity. In the proton conducting electrolyte, we want to achieve the high proton conductivity. But in the reality, the conductivity can be limited by the grain boundary, because this boundary, is between two different grains, right? Between these two grains, there is a depletion layer of the oxygen vacancy, and also the positive, which is positively charged. And this depletion layer is called charge space layer. This layer can limit the transport of the oxygen ions and also the protons. Eventually, it can affect or reduce the overall conductivity for the electrolyte materials. And this impedance also shows that how the grain boundary can affect the overall conductivity, because when the sintering temperature is increased, you have the less grain boundary. When you have the less grain boundary, you have the less resistance, and then you have the higher the conductivity. So we want to increase the grain size of during the sintering process, but it's not easy to densify. So for this work, we proposed a very new strategy to sinter the electrolyte materials at significantly reduce the temperature without any sintering aid. So we can fabricate a very clean electrolyte materials, because when the temperature is very high, you cannot avoid the diffusion between each layer, and that diffusion can cause some problem within the electrolyte, such as some formation of the impurity within the electrolyte, or even some stability issue during the long-term operation. So here we, this is unpublished work. We already submitted to a journal, for review. So we make use, in general, we make use of the ceramic shrinkage power from the electrode support to facilitate the shrinkage of the electrolyte, because the electrode, for the electrode is, support is thicker. The electrolyte membrane is thinner, around about 15 or 10 micron. So if we can use a very sintering active electrode substrate, and then we can, during the temperature heating process, that kind of the shrinkage force can help the densification of the electrolyte. So this is just a kind of hypothesis. So we measured the shrinkage behavior, and as shown as the left-hand figure, we compare the different kind of electrode materials, and then we choose one which can be compatible to the shrinkage behavior of the electrolyte. And also for this electrode support, it should be very sintering aggressively. This shows the sintering result. As you can see here, the electrolyte is very, very dense. So as figure B showing that it's this electrolyte layer is consistent of the different grains, right, together. So we want this grain as big as possible. And we also examine the user TEM, scanning from the electrode layer to the electrolyte layer to show there's any kind of element diffusion from, from the electrode to the electrolyte, and we demonstrate that it's pretty clean. And because of this clean electrolyte, we have no any contaminant, so we can achieve the intrinsic conductivity for these materials. So this figure shows some, very promising electrochemical performance, in both fuel cell and also electrolysis mode. So I don't want to introduce too much here. I just want to say that we compared the performance for the hydrogen production, for the electricity generation. We compared all the results with the literature, and then we show, based on the same materials, and we show that we achieve the highest performance. And this work is still on the way. We want to further optimize the performance. And next one is the interface, improvement. This is very, another piece of work conducted by our graduate student in Idaho National Lab. And here, in very short. So we use an acid method, to corrode the electrolyte surface, because normally the electrolyte surface is very smooth. So when you fabricate another oxygen electrode on the surface, we have some issues with some, easy delamination because they are very smooth. So we use acid to corrode the electrolyte surface to lead to some very coarse, very rough surface, and then we apply, the electrode layer onto this electrode surface. After applying the electrolyte, we examine how easy we can peel the electrode off the electrolyte surface. So we examine the peeling force between the electrode and the electrolyte. After the acid treatment, we can see the increase of the peeling strength. Because of the increase of the peeling strength, or we can say that the stronger bonding strength between the electrode and the electrolyte. And then we can see very, higher performance and also the stability. This shows the comparison between the untreated and also the treated electrolyte surface. You can see very, obvious, difference between, two samples. And next one, is I want to briefly discuss a little about the three-dimensional electrode structure synthesis, and also something, we call it the hydrogen beyond, not the hydrogen production. Yeah. So here shows some, we call it self, architectured synthesis, or we call it template method synthesis of the electrode materials. So this is a very powerful electrode, structure, which can be compatible of, high gas flux for the reaction, and also for the integration of the other kind of catalyst, for different reaction. So how we fabricated this kind of mesh structured electrode. So this slide shows some, processing. So we use some kind of template and rinse this template into the solution. That solution is contains all the, components for the electrode materials. And after rinse for a while, we take it out and then we file it, and then we get the, mesh structured, electrode, and which has very high porosity, and we can easily scale up this kind of mesh-like electrode. So here shows some examples of this kind of 3D electrode to be applied for the fuel cell and also for the hydrogen production. So the performance can be significantly improved, because for each for each mesh, it consists of the nanofibers, and for each nanofiber it consists of the nanoparticles. So if we enlarge by the TEM, you can see as showing in figure D and E, so it's very small particles. So it's very active for the reaction. Next one is I want to show that we are not going just to do some work on the lab scale. We also want to scale it up. So here shows some of my previous work in Colorado School mines. We can also build some small SOC stack. So we can stack different layers together to form multi-cell stack for testing and evaluation. And eventually, this figure shows some, bigger system, established in Unreal. I just want to show as an example. So my plan is that if we can also build this kind of facility in OU, so we can examine, or evaluate the performance, for different sides of the SOC system, not only the SOC system, but also extended to the PM, the low temperature electrolysis cells. And for the hydrogen beyond, I want to say that SOC is not just only for the hydrogen production for the fuel cell, but it also can be used for something else. For example, because this electrolyte can conduct either proton or oxygen ions. For example, for the proton conducting electrolyte, we can be used for the dehydrogenation reaction. For example, if we can introduce some ethane C2H6, into the one electrolyte, and then we have the proton transfer the electrolyte, we can synthesize the ethylene and the hydrogen, right? And we can also use SOC for the protonation reaction. Actually, we can also say this is a hydrogenation process. So for example, we can use it for the CO2 reduction. For example, if we have the protons from the water splitting, why we cannot make use of the protons by reacting these protons with the CO2 to form some hydrocarbon molecule, something like the forming acid, and such as methanol, right? This kind of useful chemicals. And we can also use it for the ammonia synthesis. If we can introduce the nitrogen, plus some catalyst, can we enable the reaction between the nitrogen and the proton? Eventually, we want to synthesize the ammonia. And this slide shows some, another process which is called Mda process, which was a project, I work as a PI in Idaho National Lab. It's called Mda, methane dehydrogenation. So it's a quite simple reaction here. We use the natural gas, which is methane, as a feedstock, and on the catalyst, we can convert this methane into the benzene, which is aromatic, and also the hydrogen, right? So we have developed some very high performing catalyst for this for this processing. And what else? For the hydrogen beyond, right? For the oxygen ion conducting, we can also use SOC for the methane dry reforming. As you can see here, if we have the methane feeding at one side and then CO2 at the other side, the methane can be converted into CO, carbon monoxide, and then oxygen trans through the membrane to oxidize sorry, it's wrong. Yeah. Firstly, the CO2 is converted into the CO, carbon monoxide, and also the oxygen ion. And the oxygen ion can oxidize the methane to further form the CO and the hydrogen with the syngas. And also we can use for the steam and the CO2 co-electrolysis. So as a figure showing down there, if we can feed the steam and the CO2 at the same times, both molecules contain the the oxygen, right, ions. So if we can, have the oxygen ion transfer through the other side to form the oxygen, and then we can form the hydrogen and the CO at the one side. If you know some news from the NASA recently, they launched the, to the Mars, right? They actually loaded a CO2 electrolysis modular.
Hanping, I suggest that we cut it short because we need to have questions and answers.
Oh,
So
yeah, sure.
if you could.
Yeah, almost done. It's just done.
All right.
So here is a conclusion or the summary for all the, thing I talk today, basically the hydrogen technology, for hydrogen technology, we have a lot of opportunities, but at the same time, we have some challenges on the materials, on the scaling up, on the efficiency, and also the integration, and also the cost, which is very complicated. That means we have a lot of opportunity to address these issues. So yeah, here I want to acknowledge the DOE funding, the funding from Idaho National Lab, and also the OU College of the Engineering, to make it happen. So, right now I'm open for any questions from you guys.
All right, well, thank you very much, Professor Ding. So the floor is open to any questions. We have about 10 minutes. So probably want to start with shorter questions, and then if people want more in depth, we can do those. I guess if nobody else has questions, can you go back and talk a little bit more on the self-sustaining system that you mentioned earlier?
Mm-hmm. Yeah, go ahead. Yeah.
So I apologize, it's been a minute since I've done any physics, so I'm very rusty on most of this, but it can generate both electricity and a hydrolysis, I guess?
We cannot say at the same time, and if you can see the bottom figure, I need to switch the operation mode between the electrolysis mode and the fuel cell mode. By changing the voltage, you can see, for example, for the bottom figure, you can see for the black line, right? You can see 0.8 volt and 1.3 volt. When it is was 0.8 volt, that is under the fuel cell mode. That is for generating the electricity. So the current density is positive. And then if I switch it to the 1.3 volt, that is the electrolysis mode. And then the corresponding current density is negative. So that's producing the hydrogen. So this can be controlled by the instrument, I'm not sure I answered your question.
No, I was just kind of more interested in it because it seemed kind of interesting.
Yeah, this is kind of dynamic process, dynamic. You can, I want to check the cell's robustness, by dynamically changing the voltage, and also, between different voltage, and also different temperature. So.
Okay, thank you.
Yeah.
I see we have another question from Dr. Prakash.
Hi, I have a generic question because I should confess that I'm not an expert in this field,
Yeah,
and it's as Rachel rightly told, the core knowledge of physics is rusted for most of us. But the general question what I had was that you told about the scale up for manufacturing, right?
Yeah.
So I was wondering, like, if you go to any manufacturing or any company, or maybe for VC funding, or maybe funding from a company or transfer of technology to a producer, they will ask about the technology readiness level, what is called as TRL, right?
Yeah.
So TRL is something which is very well known to us, but maybe you may not be that familiar. Are you familiar with TRL? And if so, can you tell a little bit about it? What TRL level it is? Is it at 1 or 2 or 3? And where you plan to take it even before going to industry?
Oh, yeah. That's a very good question, I think specifically for the high temperature electrolysis technology, I think, right now we have several industry, from the US and also from the Europe, they spend a lot of money on scaling up, and such as in US, we have the fuel cell energy, from Connecticut, and we have the balloon energy from the California, and we have the next series from the Ohio, and we have different vendors, they can produce the SOC device. Currently for the TRL level, I think it's almost around maybe between 5 and 6. Maybe I'm not right? Because I'm not a person from the industry. But I think, it's very close to commercialization for now. Yeah. And also from the Europe, I think they advocate the manufacturing, particularly like the Topsoe, which is a company specifically working on the solid oxide, cells, and they can, if I remember correctly, they can manufacture the cell, the planar cell with a size more than, I think, 50 centimeter by 50 centimeter, which is almost 4 or 5 times of the current, popular size, industrial size. So I want to say that, for the manufacturing, depending on the material system, particularly for the conventional oxygen ion conducting SOC, is kind of already there. Another type is a proton conducting SOC. So it's still in the early stage. So for the industry, they have not completely adopted this material system. So as I know that there was a RPRE project, in the Colorado School mines, and in the phase 2 project, they send the material to the fuel cell energy for the manufacturing and for assembly the stack for testing. I talked to that person from the company, and they got some issue, but they still demonstrated some short stack, So from the, as you said, that we still need some more investment on the, technology acceleration. I think for DOE, they also spent some money on the national labs on addressing the issues during the manufacturing of the proton conducting SOC.
Thank you. Thank you very much. That answers my question. And I should say that if by pure academics you have achieved between 5 and 6, it's a great achievement.
Yeah, 5 and 6.
Normally academic level lab experiment doesn't go beyond 3 or 4. So that's a great achievement. Thank you.
Yeah, thank you. Mm-hmm.
All right, I think Suruj Patel has a question.
In one of the slides, that AFM of electrolyte after processing, in that one, there is surface roughness increases after the processing. So this is something I think you mentioned, peeling force. So is it due to the penetration of this electrolyte in anode or something else?
Do you mean the different current density for the electrolysis mode and also the fuel cell mode?
Sorry, I'm not understanding.
Yeah, can you explain your question a little more? Yeah. Mm-hmm.
So in one slide that shows the AFM to show the surface roughness. of
Oh,
electrolyte.
the
in
another
one
slide. You are
process.
asking another slide. Okay.
Yes.
Yeah. Yeah. Go ahead. Go ahead. The AFM.
Yes.
Mhm.
So in that one, that surface roughness increases after processing.
Yeah. This one.
Yes, this one.
Mhm.
So this surface roughness increases. So this increase in surface roughness is due to the penetration of electrolyte in anode, or something else is the reason.
Oh, yeah. So I think it's pretty simple. It's not because of any penetration. It's because we use some nitric acid to corrode the electrolyte. Because
Oh.
this electrolyte is metal oxide. So the metal
Mhm.
oxide actually can react with the nitric acid. So if we can apply the nitric acid on the surface, it can react
Okay.
with electrolyte materials. So depending on how long we treat the electrolyte surface, we can control the roughness of the electrolyte.
Okay.
Yeah.
Okay. Thank you.
Yeah. It's not that complicated.
Oh.
Mm.
Yes. Thank you.
Mhm.
All right, do we have any further questions for Professor Ding?
Yeah.
All right, if not, then I think we are good to close out. Thank you so much, Professor Ding, for your talk.
Yeah.
The recordings will be available on our YouTube shortly. And I guess if anybody has any further questions, feel free to email. I guess that's it for now.
Yeah,
Thank you,
so
Dr.
much.
Ding.
Yeah,
Thank you.
thank you so much. Yeah, feel free to stop by my office if you have any question or interest. Yeah.
Sure, sir. Thank you so much.
Mhm.